So, welcome you to this module 2. In this module, I will give you a brief description about parametric estimation problems. So, let us look at what is a typical scenario in parametric estimation problems. So, what you have is you have x1, x2, xn, a random sample or a sample just, and suppose your x, which is the total data denoted by a vector x, and suppose this has a distribution function f, which belongs to certain family f theta, such that theta belongs to capital theta. I am interested in goal is to estimate mu of theta. So, some characteristic or some function of theta based on x1, x2, xn. So, based on the data which you have. So, what do you do? What you need to do is you need to give some estimate of mu of theta. Now, this mu of theta could be vector valued as well. It could be real valued, it could be vector valued. So, the possible range of mu theta could be R, R2, R3, it could be in general Rn. So, what you need to do? You need to give an estimate of mu theta based on x1, x2, xn. So, or in other words, I want to give an estimator. For mu of theta. So, that is what I want to give. Now, in the first course, normally you would have said an estimator is nothing but something which just depends on the sample values x1, x2, xn. So, in your first course, delta of x. So, what you have is a delta from Rn to R. So, what you say is if your x is observed, delta x immediately gives you an estimate of mu of theta. What I will do is I will give a much more general definition of an estimator. So, what I do is I define a randomized estimator. So, the name randomized comes from the fact that if you look at in this scenario, what is happening is immediately after you have observed x1, x2, xn, you are arriving at a decision or you are arriving at an xn, which is nothing but delta of x, and this xn delta x corresponds to the estimate of mu of theta. What happens in the case of randomized estimator is after observations x1, x2, xn have been taken, I do not immediately go for my xn. I may perform another randomization or another random experiment before I give you the final estimate of mu of theta. For example, x1, x2, xn, suppose are IID normal theta 1. So, theta belongs to capital theta, which is whole real line in this case. You know that mean of a normal distribution can take any real value. And suppose goal is to estimate mu of theta, which is just theta. So, I am interested in estimating the mean of theta. So, if I have to look at this kind of estimator, my delta x could be 1 upon n summation I is equal to 1 to n xn. So, in this case, I do not do any randomization. Immediately after my sample has been taken, I say calculate the sample mean and take that as an estimate of the population mean. Somebody else may say that, look, because sample mean may sometimes vary a little bit here and there, so I don't want to, I want to ignore that kind of a bias. So what I do is, after x1, x2, xn are observed, calculate sample mean. I do not take this sample mean as an estimate. Rather, what I do is I go back to my computer and I generate one observation from a normal distribution with mean same as the sample mean and variance 1. So generate an observation y of x, but because it depends on what you have observed. Y depends on x, y because it depends on what these xi's are. Normal with x bar and 1. So after you have observed x1, x2, xn, you know the sample mean. So what it says is, now you generate one observation from a normal distribution whose mean is same as this sample mean which you have observed, and variance is 1. And I take yx as an estimate of theta. So let me first here, this you must have done in your earlier course, but let me just make a small distinction between an estimate and estimator. As you know, estimator is always a random variable. So you study the property of estimator because it depends on random quantities which you do not know in advance. Any observed value of estimator is called an estimate. So that means after you have observed what are the values of those random variables, and then you calculate the estimator based on those observed values of random variables, that you call as an estimate. So in other words, estimate is just a realization of an estimator. Realization based on what you have observed after getting the sample. So I take, so basically here it would be yx would be an estimator of theta, y small x would be an estimate of theta. So this would be estimator of theta, and suppose y small x which I observed, so if, because this x represents a capital random variable which I haven't observed. What I have observed it is realization which could be small x. This is called an estimate. So what is happening in the randomized estimator? In the randomized estimator, after the sample has been taken, I do not immediately get my estimate, rather I get a random variable, a further randomization I do, or in other words, I get another random variable yx, which has certain distribution, and then I take an observation from here. In other words, what it means is, after I have observed x1, x2, xn, I get a probability measure, which in this case is x bar and 1, which depends on what your observed sample is. And then I get an observation from this. So basically, what I am saying is, after I have observed x, I get a probability measure, because that is what is happening. You are getting an observation from that probability measure. Getting an observation from probability measure is equivalent to knowing the probability distribution. So in other words, what I can do say is, a randomized estimator delta is a map from sample space cross chi. So for every, or in other words, to 0, 1. So with the following interpretation, that for every this sample space, if you want to have it in generality, you can have it in Rn. So for every x belonging to Rn, delta dot given x is a probability measure So for example, what was happening in this case? What is the randomized estimator over here? For every fixed x, my probability measure is nothing but normal distribution with mean x bar. So for example, delta x could be, so example in the last case would be delta of a given x is same as probability that normal x bar 1 takes value in the set A. So it depends on x, because x bar. And that is what is happening over here. Which in fact, if you want to write down in terms of the random variable yx, which corresponds to this probability measure x bar, in this case, this yx corresponds to this probability measure. So this is nothing but probability that yx belongs to A. So this is a randomized estimator. So what does randomized estimator says? It says after you have observed x1, x2, xn, you do not immediately take the xn. After you have observed x1, x2, xn, you observe another random variable y which depends on x1, x2, xn, and whose distribution is given by delta dot x, and I call this delta dot x to be the randomized estimator. Now, these kind of estimators can be considered as particular case of randomized estimator. Why? What was happening over here? After I have observed x1, x2, xn, I say immediately take x bar. So no further randomization was involved. So that means after x1, x2, xn I have observed, I take x bar with probability 1. But x bar with probability 1, which is a degenerate probability distribution, itself is a probability distribution. Itself, it is a probability measure. So in that sense, non-randomized estimators are the one for which this delta dot x is a degenerate probability distribution, or in other words, in that case, yx takes only one value with probability 1. So non-randomized estimator so delta for every x, delta dot given x is degenerate. What does that mean? Or in other words, for every x belonging to Rn, so this delta dot x is the probability measure of random variable yx. So in other words, for every x belonging to Rn, my yx only takes one value with probability 1. So that means for every x belonging to Rn, there exists that value which yx assumes is probability 1. So there exists a ax belonging to A. Of course, this has to be in the xn space, says that probability that yx is equal to ax is 1. For example, in this case where I was talking about non-randomized estimator, which is same as sample mean, my ax could be one by n summation I is equal to 1 to n xi. So what it says, after you have taken x1, x2, xn, Your random variable takes only the sample mean with probability 1. So that means you get, after x1, x2, xn has been observed, you take sample mean only as an estimate. So that is what it means. So in that sense, randomized estimators are much more general than non-randomized estimators. Now let's move further. Let us talk about the loss function. Now note that any estimate which you are proposing based on x1, x2, xn is based only on a partial information x1, x2, xn. So there is some error contained in what you are proposing, because it is only based on a partial information about the whole population. So that means every xn corresponds to a loss or a gain depending on what is the true unknown value. So I have a loss function L from theta cross A. I always take loss to be non-negative. Loss should be always bounded below, because loss, having a loss minus infinity doesn't make sense, right? That means there is no loss. And you are in a very good situation, but that never happens, because there will always be some error involved. So, and once it is bounded below, you can take always it to be bounded below by 0. So my loss function is L theta A. And what is the interpretation? L theta A loss in taking xn A which is belonging to this xn space A, when, because true state of the nature I do not know. So the true parametric value I do not know. So when theta belonging to theta is the true parametric value. Now in the statistical decision theory, this is also written as when theta is the true state of nature. I'll explain you how does the nature comes into this whole discussion. So in decision theory, what is said is a statistician is playing a game with nature. Nature knows the correct situation. So nature knows what is the exact situation, or he knows the true state of the nature. What statistician is trying to do? It is trying to guess what is the true state of the nature. So he's playing game with the nature. Nature knows what is the true state, and statistician is trying to guess what is the true state of the nature. So suddenly when you are guessing, you are bound to make mistakes. You are bound to make errors. And that error is captured in this loss, L theta A. So this is loss in taking xn A when theta belonging to theta is the true state of the nature, or mu theta is the correct value of the quantity which you want to estimate, which we call as estimand. Estimand is the quantity which you want to estimate. So that is the loss function L theta A. So what you do? I can talk about the loss involved in using an estimator. So let's talk about L star delta or L star theta delta x. Now note that here, when you are talking about loss, there are two kinds of randomizations are involved. One randomization is when we are taking a sample x1, x2, xn, because x1, x2, xn are random variables. And if I am using an estimator, which is a randomized estimator, there is a second stage randomization which is based on x1, x2, xn. So what would be the average loss in using randomized estimator? Delta dot when x is observed and theta is the true state of nature. Now note that after x is observed, I do not take the xn as it is. I do a further randomization which is equivalent to observing another random variable yx. Now this yx, because it is random, so I take its average value. On an average, what would be the loss I will be getting if I observe x, because yx is a random. So that can be given by L theta yx, where this yx is nothing but random variable which corresponds to the non-randomized estimator, which is also a probability measure, delta dot x. So this is what take care of second stage randomization due to the estimator delta dot for given observed value x. Now I talk about further average of this average loss, which we call as a risk function. So risk function. R delta theta. This is nothing but, now here I do a randomization with respect to x, so this capital X is considered as a random variable. So this is same as expected value of theta, L star theta delta x. So now I do randomization with respect to x. So I take the average over this quantity when x is varying. This is called the risk function. So what normally you try to do? You try to find an estimator. Goal is we try to find an estimator which minimizes R delta theta for every theta belonging to capital theta. So I am trying to find an estimator delta whose risk is minimum for every state of nature theta. Is that possible? That is not possible. That is too much to ask for. Why? Because you can always choose an estimator which gives you a perfect value when theta is equal to 1 is the true state of nature. You see, if theta is equal to 2, so for example, if I say I take my sample mean to be 1, or I say my estimate is always 1. Now, if estimate is 1 and if true state of nature is 1, which is unknown, so at true state of the nature value 1, my estimate, which does not take even consideration of any observations, gives you the smallest risk, because estimates theta is equal to 1 accurately. So minimizing this for every theta may not be possible. So to explain what I said, x1, x2, xn, IID, normal, theta 1. And suppose my goal is to estimate theta belonging to theta. And suppose my loss function is square error. A belongs to Xn space. My Xn space is collection of all possible values of the mean theta, which is whole real line, and theta belongs to capital theta, which is also real line. So if I look at risk of an estimator delta theta, which would be expected value of yx minus theta whole square, right? So first randomization with respect to yx, there is no theta over here, with respect to yx, and second with respect to theta. Now this is always greater than or equal to 0. I know, the smallest possible, because it is a non-negative quantity. So expectation of a non-negative quantity is always greater than or equal to 0. So no other estimator can have a risk less than 0. Now I consider estimator delta dot star x, or my yx, rather than what I say is yx is always 1 for every x. So what it's saying? I am saying whatever may be the observation, I'll always say my mean is 1. Now, what is so corresponding, so suppose y star x, and corresponding probability measure is delta star. So this is my estimate. So what does my estimate says, delta star? It says after you have observed x, ignore x, you always take your estimate to be 1. Don't make it to depend on your observation. Now let us look at what is R delta star theta. It would be expected value of yx is always 1 with probability 1. So expected value of 1 minus theta whole square, it does not depend on x. So this randomization also gives you this. So this is same as 1 minus theta whole square for every theta. So what happens? This estimator delta star has risk of 0 at theta is equal to 1, and it has a very small risk in the neighborhood of theta is equal to 1. So R delta star 1 is 0, and which is always less than or equal to risk of any estimator. So if you have an estimator, now this 1 you can keep on changing. You can have another estimator whose risk is, which always estimates by 2. Then its risk of such an estimator at 2 would be 0. And any other estimator would have risk greater than risk of the estimator which is estimating always by 2 at the point theta is equal to 2. This would be always 1. So that means at any given point 1, you have an estimator whose risk is smaller than the risk of a given estimator. So that means if there has to be a best estimator, its risk should be 0 for every theta. Now you cannot have a risk to be 0, because this is 0 if and only if yx minus theta is 0 with probability 1, which means yx is same as theta, but then that means yx is not an estimator, because yx is same as unknown quantity theta. So one cannot get an estimator which minimizes the risk for every theta belonging to capital theta. And the main reason for that is because there are some troublemakers which are not good estimators, like an estimator which does not depend on observations and says always estimated by 1. They can make your risk very small in a neighborhood of a given point, but they are not good estimators, because my theta takes infinite number of values, and I do not know the true state of nature. It only takes care of situation where theta is in neighborhood of 1, but that I do not know because theta is completely unknown to us. So, finding an estimator which minimizes the risk for every theta is not possible. So, what you try to do is you try to restrict your class of estimators by getting rid of all these unreasonable estimators like Yx star is equal to constant, which do not depend on observation. Or you try to restrict class of estimators by imposing certain reasonable restrictions on the estimators under consideration. Now, one such restriction you did in the last course, you said you should consider only unbiased estimators. That means estimators which on an average give you the value mu of theta when used over a large period of time. Now, once you restrict to unbiasedness only, then it was possible to get a best estimator which you saw in the last course. So, it is not possible to get an estimator which minimizes the risk for every theta. So, you need to restrict your class of estimators. So, unbiasedness was one such criteria. In this course, we will discuss another reasonable criteria which is called the invariance. So, we will restrict only to invariant estimators. But before going to that, let us try to